And you have another, which is Q form. And you take exterior product, so that will give you P plus Q form. Now, by the way, the set of lambda P is the set of all P forms. So that P, of course, can be 0. These are 0 forms. What is a 0 form?
Scalar.
This is its functions, right? Scalar. One form, these are covectors. Then you have 2 forms. And so what's the highest value that P can take? N. So these are N forms. And it cannot be larger than N because they must be antisymmetric, and you cannot have an antisymmetric because there is something that has N indices, or more than N indices, and they have to be different. But they can only take N values, so you cannot have different indices if there are more than N. So that's why it is 0. So these are the only values that they take, and you actually can compute the number of components, but that's not important. So anyway, if you get P plus Q, which is greater than N, then what is it? 0, right? So you can only get, say, if you have R3, and you take a 2 form and then eventually another 2 form, then you should get a 4 form, right? But 4 form in R3 is what?
0.
0, that's why this should be 0. Okay, so let me define this, how that base product is defined. Well, if you do it, well, let me just define it in terms of the components. So the components of that, of the product, which is a P plus Q form, so it has P plus Q indices, I1, IP, J1, JQ. So it's P plus Q form. And of course, it's antisymmetric in all of these indices, right? Must be. So it's obtained as follows. So you take alpha, I1, IP, the components of that, and then you take beta. Okay, and then you just multiply it. Well, but then the product, this would give you a tensor product. But the product must be antisymmetric. So what you do, you antisymmetrize over all these indices. What does this square bracket mean? It means that you sum over all possible permutations of these P plus Q indices with the sign. And the sign is that it is +1 if it is an odd permutation, and it is -1 if it is a +1 if it's an even permutation, and -1 if it's an odd permutation of this number. Let me just give you the definition. So what does it mean? Let's say you have a tensor I1 antisymmetrization. So what is this? So you take that tensor, say P, and you antisymmetrize. So what is this? Well, this is summation over A, well, I of sigma 1, I of sigma P. I'll tell you what that sigma is. Then you get -1 to sigma, and then you sum sigma comma SP, and then you divide it. Sorry. So, what is SP? The SP, you remember what is it? It's a permutation group. So it's a finite group. The order of that group is exactly P factorial, which is there are that many permutations of P term. So you take that, so basically you take one p numbers, and you permute them, and so those go to sigma 1, sigma p, so permute them, and that's what this is. So, and you sum over all possible permutations. And then you take that with the sign. What is sign of C? Sign of C of sigma. That's the sign of the permutation, so it is equal to +1 and -1. +1 if
number of permutations.
yeah, if it is an even, and this is if it is odd of 1 p and odd permutation. So, well, basically you take that, you could introduce the notion of elementary permutation when you just permute two elements at a time. Any permutation can be realized as a combination of elementary ones. So the even one is the one that contains even number of elementary permutation, and odd one is the one that contains an odd number of elementary permutation. So you permute two elements at a time. Okay, and that gives you this. This dividing by p factorial is there because this sum includes p factorial terms. Okay? And that's why it is there. Well, and here, in that we would multiply that p plus q and divide by p factorial. I think that's what it is. Okay, just check my notes so that I don't confuse you. Yeah, probably that's right. Yeah. Well, that p plus q factorial, it'll kill that one. And then why do you divide by p factorial? Because this antisymmetrization includes in particular antisymmetrization over this. But it is already antisymmetric, so it will produce p factorial equal terms, and that's why you're dividing by that. And the same, it will include antisymmetrization over this indices, which produce q factorial equal terms. And so if you do that, then it will give it. Okay? So that's the exterior product. Now, exterior derivative. How do you define exterior derivative?
In that definition, was that -1 to the power of sine of the permutation sigma? That's the power, right?
Well, yeah, it depends. It's just a notation. Let's just do it. I mean, if you write -1, then this would be 1 or 0, not 1 or -1. Yeah, if you just put it here, then it is +1 and -1. Well, I'm not going to give you an example of, say, in lower dimensions for this, which is kind of, well, you can look at it, and there is no one you will find it everywhere. But the point is that you take a tensor product and then you antisymmetrize, you get a new form. It's a, if this is a p tensor, this is a q tensor. The tensor product gives you p plus q tensor after antisymmetrization. This is p plus q antisymmetric tensor. And that's it. Okay. Exterior product. So far we only did algebra. Exterior product, of course, that's a derivative, but not a product, derivative. So that's a kind of analysis. So what is exterior product? By the way, you can say that. Well, okay, I don't want that. But exterior derivative, it takes p form and maps it to p plus 1 form. Well, you can write this, but I guess it doesn't make much sense. So that's what the exterior product does, right? So it takes one p form, one q form, and gives you p plus q form. So here is the exterior derivative. So it increases the order or the rank of the form by 1. And how is it defined? Again, you could define it either in components or directly, but probably the simplest way to do it is this. So let's say alpha be a P form. Well, there is that. So that's the P form. And here, again, if I write this sum, well, let me put the hat on it. So sum in the hat would mean that the indices are in increasing order. So, which means I1, so it's just much easier to write hat than to write this. If I don't write the sum, then it means you sum over all. So basically, write it right. Some books introduce collective index, call this a capital I, multi-index, and you would write like this, and then all of them. That's kind of confusing. I mean, you've seen that in a Frankel's book, and maybe people did like it, and then you would put an arrow above it indicating that the indices are in increasing order. If the notation is not common, you're not going to see it somewhere else, you'll forget it, and it's confusing. So, or either use this notation, which most of the book use, or this one, which is just like, well, most physicists would write it this way. They don't like to write any sum, so. Okay, so that's the form. Then what is the exterior derivative? Well, we just write it the alpha. These are functions of x, right? Then it basically is this sum where you have d alpha. These are just functions. I'll explain what that is. It's over function, differential over function. That's all. So what is it? Well, if p is 0, then this is a function, right? F is a function. What is differential of a function? Well, it is df by dxi dxi, right? So, which means that this is a function, and then you apply differential of that. So that will give you d alpha I 1 ip over dxj dxj dx1. So that's what it is. And that's probably the easiest way to do it. Now, if you, because this is a wedge product, of course, it is anti-symmetrization over all indices, and in components, that would look like this. So, like d alpha, that's a p plus 1 form. So it's p and then j.